Imre Bartos. He's an astrophysicist at Columbia, and he's going to give us a talk on black holes and what we can learn from them without falling in.
Thank you. It's a pleasure to be here. It's a very nice turnout, apparently. So again, I'll talk about black holes in general. The reason I put this second part of the title is that one of the main interesting topics we can talk about when we discuss black holes is what would happen if you get really close, if you fall in, how we die, for example. That's something people discuss very often. I'll try not to go that far. First of all, because we have no idea. Nobody really knows. People who know never came back. But also because there's a lot of other things we can do with black holes. And what I'm interested in as an astrophysicist is all the other stuff that we can use black holes for as a tool to study the universe, as I'll mention in a second. So a few topics. Again, I'm not sure what we'll have time for, and again, we want probably questions at the end. But basically, the kind of topics I'll mention is, what is a black hole, very briefly, or for the purposes of this talk, how black holes are born. It's important to understand in order to discuss what they're used for, what they're useful for. How we know about them in the first place. Again, nobody has seen a black hole, as you guys probably know. Also, what they're used for. Again, that's what I'm mainly interested in, what we can learn by looking at black holes, about the universe itself. And I'll focus a little more, in particular, on one experiment that I'm a member of, which is the laser interferometer gravitational wave observatory, which is something very interesting because we are turning on this detector actually later this week, so it's something very actual. So I'll mention certain things about this, and then again we can steer the discussion in any direction you guys want. So I'll be happy to go in any direction. I'm also working with a bunch of other experiments, mainly high energy experiments. I'm interested in the universe at extreme energy, so there's plenty of other things that we can discuss if we have time. Before we, again, do anything, just what is a black hole? So, again, there's many things that we hear about black holes. Typically, when you read about a black hole in any journal, they are characterized as a monster that eats something. That's very often, unfortunately, with how I'm usually featured in the journals as well. It's usually black holes are monsters that eat everything. Well, that's not everything that's out there, and we can exemplify this through this thought experiment. So this is the sun and the earth as you guys see it, and let's do the following thought experiment. Let's take a magic wand and make the sun become a black hole right now. And the question is, what would happen to the earth? What would happen to us if this happened for some reason? It's not going to happen, don't worry, but what if this happened? And the answer is, we can maybe see directly, but basically the answer is not much. Well, things would go dark. We wouldn't see anything, but basically the earth would go dark, but beyond that, nothing really would happen. Everything would work the exact same way. The sun would not, or this thing here, the black hole would not suck the earth in. Nothing really happens from this large distance. It would be just like any other object with a large mass, with the mass equal of the mass of the sun. Okay, so black holes are not dangerous from this distance. We don't need to be afraid of them as long as we are at a large enough distance. And again, there's three things that we hear about typically happen, or all happen when we get really close, when we get very close to the surface of the black hole. Again, on this picture, the central thing here is a black hole, and this is how it distorts space, or distorts light from the stars and galaxies behind it. But really, unless you go that close, black holes are very nice and friendly creatures. Again, once we get close, things change in very different ways. Time changes, mass changes, how massive we are. We would get shorter, for example, as well, if we got close to a black hole. Time would pass differently. If you guys saw, have you guys seen Interstellar last year? Yeah. It's not all true, but it's there's some truth to it. So things would change if we got really close, actually. So, but again, I'm not going to go in that direction. What I'm really interested in is, again, black holes in terms of what they can tell us about the universe if we observe them, if we learn from them in this sense. So, how can we form a black hole? How are black holes born? It's not too complicated. It takes some mass and store it in a very small volume. That's pretty much what we have to do. It's not complicated. It happens fairly often. It happens every day in the universe. There's millions and millions of black holes just in the Milky Way. This is not a rare object at all. So there are different ways how this can happen. How the universe squeezes a lot of mass in a small volume. The most typical one is if we take a massive star, a very big star is something that's much bigger than our sun. Typically, we talk about 30 times or bigger stars. Basically, what happens is the inner part of the star will be unable to support, thank you, I'll be walking back, support the pressure, and the whole star collapses into well, different things, but for example, a black hole as well. So that's one of the ways. The pressure from the mass of the sun, mass of the star, will create a black hole. Okay, so again, a lot of mass squeezed into a very small space. Our sun will never go through this. It's going to go through a very different path. There's some other ways. For example, stars are sort of like humans. They are also social. They don't have to be by themselves. Most stars have a companion. The sun is an exception in this sense. And so when one of the stars dies, it's a sad story, but what happens is it can take some matter from that star, which can be either a black hole or something else, for example, a neutron star or a white dwarf. It can take some matter from its companion star and grow in its mass to the extent that it collapses again into a black hole. There's all sorts of things that happen in the meantime. Okay, so that's another channel how we can create black holes. And there's other ways. If you have both stars dead in this case, they can eventually collapse or merge into one bigger object, and if that's massive enough, then this joint mass will collapse into a black hole. So that's another typical way that's going to be important for our stories here. Another interesting aspect of black holes, you guys probably know, every galaxy, as we know, has a humongous black hole in the center. Okay, so the Milky Way does, but basically every other galaxy does have a very big, so-called supermassive black hole in its very center. It's much bigger than what we have from stars or from the other channels that I mentioned. It's not completely clear at this point how these very big, massive black holes are formed, but they seem to be closely connected to the properties of the galaxies. There has to be some interconnected behavior. One interesting aspect of this, again, as I mentioned, for the most part, black holes end up with a mass that's comparable to the mass of our sun, a few times bigger typically. But again, we have this group of black holes, supermassive black holes, that are way bigger, that are millions or billions of times more massive than our sun. But there seems to be a gap between these two. These are the two kinds of black holes that are out there, and we have a missing link to some extent. We don't have anything in the middle, which is one of the open questions in why there are no black holes like that. There may be, we just don't know about them, again, because it's hard to see these black holes. So how do we know that these black holes are out there in the first place? How do we know about any of these black holes? As probably nobody has ever seen a black hole directly. So far, that's what we're working on. That's what I'll mention, but nobody has done that before. We have only indirect evidence. And so how we can learn about where they are, how they are, again, they are black, light does not come out from them, so we can't just look at them and see them, unfortunately. We can fall in, but let's not consider that option here. Basically, we can learn, one of the options is we can learn from others' mistakes. Instead of us falling in directly, we can just wait for something else falling into the black hole. Again, once something is silent, we can't see anything there. All the information disappears. But on the way there, as matter or anything else is falling towards the black hole, it accelerates, it heats up, and it starts radiating something that we can observe. And that's the main channel how we learn about black holes, how we see where they are and what they do basically. Or that's what we can use basically for learning about other mechanisms. So basically, material falling towards the black hole, heating up and radiating is one way to know where they are and learn from them. There's another channel that's going to be important. That's through these things called gravitational waves. Again, nothing really comes out of a black hole, but it has a gravitational field that's pulling things in. And when for some reason the black hole moves very quickly, or something moves towards the black hole very quickly that's massive enough, this gravitational field is perturbed, and that can propagate outwards. One way to think about this is if I take a piece of stone and throw it in a pond, the water, where this rock enters the water, there are these ripples on the surface of the water that's created and that are coming outwards, and I can detect them if we just look at them and see them even far away. And the very same thing happens with black holes when something is dropped in the black hole, or in fact two black holes collide, for example. There are going to be these gravitational waves coming out that we can detect from a large distance. And again, for this, nothing really has to come out of the black hole. We're looking at its gravitational field. Okay, so again, if you just look at this example, as these two death stars are merging and getting closer and closer and eventually form a black hole, they emit these so-called gravitational waves that we can detect from a large distance. So that's the that's the idea how we could, in principle, directly see black holes. Now, there's a little problem with this, which is that gravity is, well, let's say the most mysterious force in nature, partly because it's so weak compared to all the other forces. We don't really know much about that because it's extremely hard to detect anything gravity related. So for if you take two black holes and merge them at some typical distance, the effect at Earth is going to be something with this number. So basically what happens if I take a gravitational wave, the effect that we can see here on Earth is the change, basically the disturbance of space itself. Distances are going to get a little different because of the change in gravity. Okay, so when we try to detect something optically, when we look at a telescope, we detect the photons, the light that comes from the stars. When we try to detect gravitational waves, when we try to detect gravity itself, what we're looking at is the change in distance. It's really the distortion of space and time. Time is harder to detect, but basically the typical distance changes that we need to detect for black holes merging at typical distances is something like this. So if I that's a relative distance, so if my height is, let's say, 2 meters, which is not, then it would change by 2 meters times this number. It's a very tiny number, right? Further, this animation, if you guys see it from a distance. So basically, not only do distances change, but distances change differently in different directions. So if a gravitational wave was passing by right here, I would get periodically shorter and taller, at the same time skinnier and fatter in the opposite direction. So it's this mutual change in the direction. And again, it's a very, very tiny effect. So you would never see me changing my height. So just to put it in perspective, if we look at the Milky Way itself that we heard about in the previous nice discussion, if a gravitational wave comes by, the Milky Way, which has a size of roughly 100,000 light years, the size of the Milky Way would change by the size of this soccer ball here. So it's a very tiny change, right? So it's not something that you would easily see something. Okay, so the problem is, how can you detect this on Earth, right? I can't look at the Milky Way and see that kind of change. I can't look at myself. I need to have a very, very precise scale to measure this kind of changes. So how can we do that? Actually, there was an indirect detection of gravitational waves. Nobody, just to give you guys a heads up, nobody has seen gravitational waves directly so far. So what I'm talking about is the near future, hopefully. But we have an indirect detection of gravitational waves, so we know we're not crazy at this, which is great. Basically, there's only one detection. So far, we looked at the two pulsars, which are rotating neutron stars at very large distances. And from how fast they rotate around each other, we could see how fast they're getting closer, which is due to their radiation of gravitational waves, due to their distortion of space. This is something that people got the Nobel Prize for in 1994, and their prediction was correct even after they got the Nobel Prize. So that's a confirmation. It's still correct. But again, the important point here is that we know that this is not crazy. This was detected by a radio telescope called Arecibo. So radio telescopes here too are extremely useful. And again, that was the Nobel Prize in 1994. Again, if you guys remember this little animation, how gravitational waves change space, that's what we need to detect. So we need to have a meter, basically, a scale that's extremely precise, and that's exactly what we're trying to do here. So this is the same sort of change in two directions, and what we're using to detect these gravitational waves, how we built a very precise scale here, is a thing called an interferometer. The idea is that we're shooting a laser beam that's split in two directions, and we measure the relative distance change in these two different axes by interfering the two laser beams. The path they take in the two directions changes based on the gravitational waves, and they're going to destructively or constructively interfere based on how this is going to change. Okay, so that's the main idea, how we can detect this, and that ends up being a very precise way to measure this, which is typically better than anything else that we can think of at this point. So this is how it looks like in real life. This is one of the LIGO facilities. Now, of course, if I want to be more precise, I need to build a bigger detector. Bigger is better. This is a 4-kilometer, roughly 3-mile long arm laser beam in both directions. Okay, so we shoot laser beams in two directions, and we measure how the distances change, again, because the space is distorted due to the gravitational waves. in these two directions. There's an identical detector in some different setting. The previous one was in Eastern Washington. This is in Louisiana. It's the exact same telescope or detector, except it's somewhere else. Again, notice that people are not looking in any direction. There's nothing that you can look at. It's really a measure of distance. Okay, so there's nothing you can. If you go there, you can't really do anything. It's kind of boring. There's even science saying you can't run too fast because it's a very sensitive measurement. And again, as I'll mention, it's in the middle of nowhere for a reason because it's very sensitive. So it's an excellent summer internship.
Do the wavelengths change?
The wavelength of what?
Of the gravitational wave?
It can change, so it can be any kind of wavelength. So basically,
but at the point, let's say two neutron stars collapse.
Yeah, exactly.
Is it a tighter wavelength there than it is, a million light years away where we're detecting it?
So there's a redshift, just like for light.
Okay.
It goes through the same redshift.
Okay.
I would say redshift is not as significant as the changes due to just the dynamics, right? So the closer the two neutron stars or black holes are to each other, the faster they rotate, and the faster or the higher the frequencies in this sense. It's basically the same as in any radio telescope or any kind of iPhone. Basically, how we communicate is we take little electrons and we shake them, we move them really quickly, and the electrons accelerate, and that creates the radio waves that we communicate with. Then the same thing is true for gravity. There's no fundamental difference. If I take some black hole and I shake it, then it's going to emit the gravitational waves. And the easiest way to shake a black hole is to emit a black hole. So that's how it works. And the faster I shake it, the faster the higher the frequency of the radiation.
So can we determine by the wavelength how far away the occurrence was?
By the wavelength, it's a little harder. It's easier with the amplitude. So for black holes, it's more complicated. There's all sorts of black holes. But for neutron stars, which is one of the best stars that can form, there's a very narrow mass range of where they are. And you can basically take these two neutron stars merge and create these gravitational waves. You can reconstruct from the strength, from the amplitude of the gravitational wave, how far this probably happened. That's a more important sign. But you can reconstruct that not from from a combination, I would say, of the frequency and the amplitude.
Mm-hmm. Do you have calibration issues in knowing what your distance is? Because those distances are subject to environmental changes.
You mean this distances?
Yes, those distances.
Yes, it's a very important thing. Calibration is a huge thing for this. Actually, so the next thing I was going to talk about is noise in general, which is the same part. Basically, there's various things you can do. The absolute distance of the two ends of this laser beam doesn't really matter. What matters is really the change. So that helps you a little bit. But there's many things you have to do. But I would say a bigger problem, or this is a part of the problem, which is the whole thing here moving for other reasons, which is not connected to gravitational waves, right? So the fact that this is such a small effect is one part of the problem. The other part is that other things happen, and again, that's noise that's not just intrinsic to the detector. This is one of the examples of traffic nearby. Not just this extreme, but traffic in general is extremely bad because it moves the ground, it shakes the ground, and it moves the whole detector. And we were talking about these very tiny changes. Anything that shakes the ground is problematic. If somebody comes really close, that's even worse. But
rumble of the
rumble, exactly. So
volcanoes around the
volcanoes,
world.
yeah, exactly. Any kind of earthquake is really bad. So if there's a bigger earthquake, we have to stop the detector. Again, so these arms are 4 kilometers long. Over this, the distance changes we are trying to measure are much smaller than the size of the atoms that are built that build up the detector. So any kind of motion is bad, right? So you have to make sure everything is far away, right? So as you see nothing, right? Because there's nothing there. It's the middle of nowhere, exactly. Both of these things for this reason, right? Has to be far from everything.
What's the expected frequency of a gravitational wave?
Excellent question. I missed those slides. So basically, when you talk about black holes, it's one question. When you talk about gravitational waves in general, that's a slightly different question. You basically expect gravitational waves from all sorts of things that move mass around a lot. So even starting with the Big Bang, you've probably heard of the announcement and then the announcement last year of somebody finding gravitational waves. So the Big Bang itself, the first part of what we know as the universe, as we think of it, now it probably emitted gravitational waves as well. That's very low frequency. I wish I had the slides here. So that's below nanohertz, I would say. The other part that you can have, if you look at those very big, massive black holes, supermassive black holes in the center of the galaxies, when two galaxies merges, and the black holes merge in the center, that's going to be very low frequency. That can go down to, again, nanohertz frequency ranges. Now, I would say the most interesting part, what I'm most interested in, is the stellar mass black hole mergers, or when they are formed, basically, and that's going to be basically the frequency range that you can hear. So from, let's say down to 10 hertz to, let's say, 10 kilohertz or so. So it's actually a nice thing that it's the exact same what we could, in principle, hear. We can't hear gravitational waves, unfortunately, but if it did, it would be the right frequency range for the typical black holes that are formed. So that's a lucky coincidence. So what it means basically is that, actually I'll just come here. That's my next slide, so I should have just showed this instead. So this is I'm not going to have too many of these plots, but basically this is a plot that shows our sensitivity as a function of frequency. So we built this detector to the size and to the extent that it's the most sensitive to the merger of two black holes, which is again this 100 hertz to 1000 hertz and around that basically. And we have to get rid of different sources of noise in this frequency range, which is different based on what frequency you're considering, right? So what we're seeing here is the level of noise, the higher the worse, and the frequency at which we deal with that noise. So it's 1 hertz to 10,000 hertz. Okay. So for example, one thing we can look at, and this is the different contributors. One of the contributors, for example, is residual gas. So if we have these laser beams that we want to measure the distances with, if there's any gas in the way, that's going to scatter the laser. So we have to get rid of it basically. So what we basically built the biggest vacuum chamber on Earth actually to accommodate this. So again, we have this 3 mile long laser beam, and it's put in this 2 meter wide tube that's all vacuum, very high grade vacuum to again make sure that the laser is free to go and nothing goes in the way, not animals but gas, right? In fact, we had a lot of problems. Mice end up liking the top of this tube, and when they defecate there, that's basically can go through and then it's dangerous. Anyway, there are different animal problems. There used to be an alligator at the. It was not good at the end. Anyway, lots of different things. So that's one of the noises, for example. Another thing is this thing called a shot noise. Have you guys heard of shot noise? That's something that's important for some parts of astronomy. Shot noise. Yeah. No. So shot noise is when we turn on the radio, for example, we hear shot noise as well. It's basically due to the fact that when we have any sort of light, it's not a continuous source of light. There's really photons. There's really elementary particles that build up with light that are not infinite in number. And if we have something that's not super bright, then there can be fluctuations in how many photons hit some surface per second. Okay, so when we have this laser beam and we're shooting at some surface, the number of photons per unit time that hits the surface will vary, and that will contribute to a noise. So if you're trying to measure this very precisely, that's going to be an effect. Now, the shorter time I want some photons to hit the surface, the less photons I have per unit time, right? So this is going to be a more significant effect as I go to high frequencies, shorter time periods, right? If I go to infinitely short, I'm going to have 1 or 0 photons per that short period of time. Okay, so that's something that's important. There's an easy way to deal with this. Build a strong laser, just more lights. More is always better in this sense. So that's an easy solution. Seismic activity, very important again when this core crashes. It's also seismic. Seismic is typically low frequency. Basically, we isolate everything, put everything on a nice table that filters out when the Earth moves. It's not bulletproof if you have an earthquake, for example. It can be a problem. But basically, there are these sophisticated ways to deal with different kind of contributors to our noise, to our background. Again, that's what you need. That's why it took so long to build the detectors, because you have to accommodate such a weak signal. Okay, so. One of the complicated things. The other thing we have to do is to build multiple of the detectors. Now, why is that? Have you guys heard of the cocktail party effect? Have any of you guys heard of the cocktail party effect? No. You've been to cocktail parties, not
Nerds here, they don't
So the cocktail party effect is that we're in a cocktail party, of course, and if I'm talking to somebody, there's many people who are talking in a room, but somehow I can focus on one specific person if I want. So if I'm talking to you and I'm not that interested for some reason, I can listen to somebody else. I can focus on, my brain is really good at filtering out all the noise and just focusing on a person whom I'm interested in for some reason. Okay? And it's not trivial, it's extremely hard to do. If you wanted to do it with a computer, it would be very, very hard. So we are very good at this for some reason. Apparently it's an evolutionary advantage to be at cocktail parties. And the same thing is true for gravitational waves. Okay, so there's plenty of things in the universe, there's plenty of things on Earth that are happening. And basically the reason we can do this, the reason we can focus on one person is because we have 2 ears. We identify the location of the person and we use the difference in what we hear in our 2 ears. If you close one of your ears and try to do this in a next cocktail party, it's not going to work. It's very easy, it's an easy experiment, and it may be worth doing. The same thing is true for gravitational waves. We need multiple observatories to focus on the person or the black hole in this case that we are interested in. Okay? And well, the US, we have these 2 detectors at Hanford, Washington, and Louisiana, Livingston, and Europeans are trying to catch up. There's one Italian detector, there's one German, and there's a few other ones that are being built right now in Japan, India, Australia. Everybody wants a part of the pie at this point. So there's plenty of detectors, and again, the idea is that we are more sensitive. Again, the other reason is if we have an airplane, for example, here, that's also bothersome. But if there can be an airplane at the 2 sides at the same time. So that's a way to filter out the noise again.
You can't fly these in space?
You could fly these in space. I'll have a slide of that in a second. Let me go there. I have a slide. I'm sorry for jumping forward. Yeah, you can have this in space. This is not a real image. This is just an artist picture of what may happen in the future. You can easily do this. Now, the main problem is that space is expensive, and having such a thing in space would be order $1 billion. And at this point, we don't have that much money, unfortunately, in the future. So this is scheduled after, something like this is scheduled after, well, optimistically after 2020, which is more like 2035. Not on my schedule at this moment. But it's very interesting. We're going to do this in the future, and there are advantages. So as you, that was probably the reason you thought of this. So that gets rid of a lot of the noise sources that you are dealing with. You can also build something much bigger. You don't need to deal with vacuum issues, for example. So it's very advantageous for many reasons. And these kind of experiments will be very useful to study, for example, supermassive black holes. So that's one direction that we're going in. Again, it's a farther sort of plan, partly because of the cost, other part because nobody has seen this before. So I guess if I were the funding agency, I would say like, well, at first see something, at least, and then we can talk about this, not until then. And I think that's what's happening. But before we get there, what's actually current and what's important is that we're actually turning on these detectors. The first detectors are going to hopefully see gravitational waves. I think later this week. I wrote later this month because I'm not 100% sure, but I think this Friday. So fingers crossed, and it's happening right now. So you can hopefully hear about this very soon. I will not expect to see something, a black hole, right away. It takes a while. They have to be close enough so the signal is strong enough and they don't merge, they don't form that often, unfortunately. But I would say 2-3 years from now, we will certainly have a detection. That's my prediction. I'm happy to bet with. I already have a few bets actually. Okay. So, but again, that's happening very, very soon. So it's so stay tuned. I'm sure if you read any of the science magazines, there's going to be plenty of stuff on this.
How do you determine what black holes or neutron stars or whatever are actually?
Very good question. It's a mass difference. So a neutron star is basically that star. What happens is if there's enough mass in a star that's not supported by its internal fusion, it can collapse into something. If, for example, for the sun, the sun does not have too much mass, so there's not going to be a real collapse. If the sun runs out of fuel, it will shrink a little bit and it will become something called a white dwarf. It's white because its temperature will go down to the extent that it's going to have a white color. it's a dwarf because it's going to be roughly the size of the Earth. It's going to be fairly small, actually. Not super small, but fairly small for stellar standards. If you have a bigger star, when it collapses, it can collapse into something where the atoms can't stay as they are, so the electric force cannot support the gravitational pull of the star, so it's going to collapse into a ginormous nucleus, which you call a neutron star. But it's really one big nucleus. And that happens at some specific mass scale. Basically, the maximum mass of a neutron star, where the nuclear forces can still support the gravitational pull, is roughly 1.5, 1.4 times the mass of the sun. So if you see something on that scale, you know it's a neutron star.
So you identify beforehand that you know which one's going to be producing the gravitational wave that you're measuring?
Depends on what you're dealing with. So if you look at a star and you predict that this is going to collapse into a neutron star or a black hole, well, good luck, it's going to take 1,000,000 years. So that's not a way to go, right? What you can do, you can look at something, for example, two merging things, and you can say that, well, I can reconstruct what the masses had to be for them to produce this gravitational wave, and I can tell that that was a neutron star and a black hole, or two neutron stars or two black holes, or something like that. Okay, so I can reconstruct it afterwards. Now, what I can also do, what they did, for example, for the interact detection that I mentioned, the gravitational waves, they looked at other means of identifying these things. So a black hole will not produce things like a pulsar. A pulsar is a neutron star that works like a watchtower. It basically emits radiation in one specific direction, and it's rotating, and so basically just like a watchtower. And so you know that that's a neutron star because you can identify that from, again, other means. And if something else happened to that, then you would know that that happened because it was a neutron star. But for the purposes of gravitational waves, it's the mass that tells you everything about that. Excellent question. So all this is integrated. Again, it's just like a sound. You could, in principle, there is a website which I highly recommend. It's called blackholehunter.org, and you can hunt for black holes, and I think they have some neutron star examples. You can actually hear how it would sound like when these things merged, and you can, it's a game, so you can basically differentiate yourself and see how it works, see if you're good at it or not. But it's a fun website. And it gets harder, and then there's more noise, so anyway, it's a good thing to check out, probably.
You don't need to actually aim at an object. You can detect gravity waves from any direction.
One of the perks of working in gravitational waves, right, you can't aim something like that. This is not moving at all, right? So I'm just having a scale and measure this, how distances change, and that's not going to, doesn't matter where the gravitational wave comes from, it changes independently. So that makes things a little simpler. Which is one of the other reasons, actually, why you need multiple of these, right? Because with one, it's just like your ear, right? With one ear, you would have a hard time telling where somebody's talking at you, right? So the same thing, multiple things. You can't tell the direction, but basically you don't need to rotate anything. It's a good thing. You can be far away from the observatory. You never need to go there after you build it.
Are the Legos coordinated in any way, directionally?
You mean the positions?
Yeah.
Yes and no. So okay, I would say the farther they are from each other, the better, because just like your ears, the farther they are, the better, because you have more precision in reconstructed directions. Now, if you want to build something in the U.S., then you have more limited things. If you have a powerful senator in Louisiana, then you don't have a choice, right? So it's there are different boundary conditions, I would say. But for scientific purposes, the farther they are, the better. That's why we would be excited for something in India or Australia, because it would be farther from where we are now.
The time-based
orientation, there's a little dependence. It's not, I would say it's not super important in this moment. Yeah, there is some small dependence. Yeah.
The time base would be important to you. When you want to see this in more than one place at a time?
Yeah, that's one of the reasons, right? So if you have one and just one detector, and you had some airplane, it would be hard to differentiate between an airplane and the black hole, right? If you have multiple, then the airplane is less likely to occur at the same time at the same spot. So that's one of the reasons. So in this sense, the farther they are, the longer the gravitational wave can be, so that you can identify. Yeah, so for what frequency you can identify, the distance will matter. For these two, Hanford, Washington, Louisiana, it's 10 millisecond different, 3,000 kilometers. So that's what we're working with. Typically, that's not the time base is enough. It's more of an issue of sensitivity. So it's enough. It's a good enough distance to not have two airplanes.
So in, I guess, Earth space, you're building it basically what we do to detect earthquakes, right? Throughout the world, you have a bunch of sensors and everything's synced on time. So you have a ripple on one sensor, and then you should be able to see it in milliseconds or nanoseconds later in another place. So none of our seismic sensors are directional. We just look for a ping here, and we should be able to see it.
Yeah, exactly. There's one extra complication with earthquakes, that's there's some bouncing back and forth in the earth. So it's a little more complicated, but yeah, basically the same idea, exactly. You cannot measure the direction really, and the time difference tells you the direction exactly. So I would say the time difference is more important for reconstructing the direction than in terms of noise canceling.
Is there a speed issue as to how fast the gravitational wave or effect travels?
As we think currently, it travels with the speed of light, according to general relativity. Nobody knows, and I would say the first sections are going to be useful for this as well. The limits we have currently are not really constraining because nobody, again, has detected these things so far. So I would say there are people who are working on it, like what would happen if gravity was slower. If it happens, it's wonderful. I'm not spending my research career on that, but again, it may happen. The good thing is, even if you're not aiming to figure this out, we're going to be able to tell very soon if that's the case or not. Again, if something happens at a large distance and there's some electromagnetic counterpart and the gravitational wave, if it travels over millions or billions of light years and it comes here at the same time, you know they have to go with the same speed. So we'll know this very soon.
Are these sensitive at all to radioactivity? Because Hanford, Washington is one of the most radioactive places on the planet.
Yeah,
All the bomb development.
That's exactly the reason we are there, because nobody else is there. Excellent. It's a good thing for us, actually. So it's not a coincidence. We are the Hanford, so we are at the site of the radioactive stuff, Hanford. So in the middle, actually. So we see like the nothing is like if you go a little farther, there are some nuclear sites. Yeah.
So that doesn't really have an impact on this measurement. Again,
it keeps away the competition, so it's good. But it doesn't have a direct effect. That's true. You can't swim in there. There's a river, Columbia River. You can't swim there. That's for sure. Yeah. But it's more like you're canoeing there or something, and there are signs that you can't leave the water because they're going to catch you. They keep it secret. So I don't know if it's dangerous. We don't drink the water there either. So yeah.
How long have these been operational?
You mean the nuclear sites, or
no?
So we first turned on roughly around 2000. So that's I would say the first time. It was funded in '92.
So it's been operational for 15 years.
It's been operational for, well, up and down, right? So we don't continuously operate, but it was being constructed / operational for that time, exactly. For the last, so just to put it in perspective, for the past 5 years we didn't operate at all. We were constructing the next generation. So it's advanced LIGO, and we had regular LIGO before. So we didn't do anything for 5 years, yeah, just construction.
So you're betting how many years away that they actually detect the gravity?
2 or 3.
What makes you so confident of that? Because the new one is so much better?
So there's 2 things to consider. One is your sensitivity, which you know from what you're building. The other thing is how often these things happen in the universe. And I'll actually talk about it in a little bit. There are other ways to kind of have an idea of how often, let's say, 2 black holes collide in the universe. We have other ways to learn about this. And from that you have an estimate, a rough but some estimate on how often they happen. So you have a distance at which you would see these things. You have a rate, so volume divided by or multiplied by rate. So you have a time of how, like, on average, how often they happen within the volume that you would be able to detect them in. Okay, and if you put the numbers together, again, there's lots of uncertainties. We never know, but you end up with roughly 3 years when it becomes more likely than not that you will see something. In the previous one, so in terms, and actually that's true for any observatory, any large-scale observatory that, different countries, but the U.S. definitely builds. So when you have you never build the full-scale something first because it's just too expensive and somebody could just screw up. So what you do, you build something initial that's smaller and like less fancy, but you can't just build something for the sake of building something, so you have to motivate it. And the motivation is, if it's possible to detect something, that's fine. It doesn't need to be probable. And so for our first initial detectors, it was possible to detect something. We had about a 10% chance, which is not bad. But it was probable. If you bet on it, it was a bad idea. But now we are in a probable regime. So we're not expecting detection.
Times upgrade in sensitivity was it?
Okay, so the upgrade is a 10 times more sensitive detector. Now, one interesting difference between light and gravitational waves. So if you take a star or whatever, and you put it 10 times farther, its luminosity, how bright it is, will be 100 times smaller, right? Because the brightness decreases with distance squared. For gravitational waves, it's a little different. It decreases with the distance, which is kind of interesting.
Linearly?
It's linear. It's a linear, well, 1 over linear, right? So yeah. The reason is that the brightness of the gravitational wave decreases, so the energy of the gravitational wave decreases with 1 over r squared, just like for light. But what we are detecting is not the energy, it's the change in distances. So it's sort of the only thing that goes in our favor, actually, so that's a good thing. So if you have a 10 times increase in sensitivity, then you have 1,000 times more volume. So the chances of seeing something is 1,000 times more per unit time. So that's a good thing, actually. Yeah. So it's a big difference. That's the bottom line from the previous version. And again, so that's the present or what's happening now. But again, in the near future, Europe is trying to play catch up, and so that's the next thing that is probably happening in Europe in the next, I would say, 10 years, which is a version that's underground. Underground is better because all the seismic stuff, all the car things, etc., is removed, right? So you have a much better sort of seismic noise if you go underground, and that's something that may be happening again in the next 10 years in Europe. It's called the Einstein telescope for various reasons.
When is it going to be?
We don't know. Germany is pushing it. We'll see. It's also money related, I guess, but it's not clear. Europe is looking at different sites, and they're trying to see which site works the best seismically, and then they're going to weigh it with some contribution from the country. As always, it always works like that, actually.
The cyclotron is not stable enough for you to detect change in the angular momentum or anything like
that? The problem is when you involve any sort of electromagnetic interaction, just like in a cyclotron, there's a 100 billion times difference between how strong the electric forces and the gravity is. So it's going to be extremely difficult to actually 10 to the 20. It's even more. There's a huge difference between the two. So if anything, if there's a time, you can't be that precise with electric stuff. So it's just not going to work. You have to have something that's completely decoupled from anything electric, which is hard but reasonable. So for example, one of the interesting things is with the LIGO detectors, just I want a picture, where is it? Okay, too far. Anyway, one of the interesting things is, so our detectors operate in the US, and it turns out that there is this one pulsar that's the brightest pulsar called a crab that's not too far, and we would be super interested in seeing gravitational waves from it. If something rotates, it could emit gravitational waves. The problem is the pulsar is rotating at a frequency which is 59.67, I think, hertz. It's a problem because the US at some point decided to have its electric frequency at 60 hertz, so it's a problem. So we're turning the whole detector into DC for this one object, which is, it's a waste of time. But anyway, so the point is, electric stuff, and if there's anything electric, it can be a huge issue. So anything that's electric will not work. Unfortunately, people have thought about this for a long time. There were different ways to try to do this scaling thing. Interferometry seems to be the most efficient at this point. Okay, and again, the space-based stuff in the next 20, 25 years, we'll see. Okay, and there's actually another way, which is using pulsars. So pulsars are, again, little neutron stars that are emitting light in one direction, and they are rotating, and it turns out that they are extremely precise clocks because they rotate with one very stable frequency. So if we look at how often we see the light from a pulsar that's far away, if there's a gravitational wave coming by, it sort of distorts the space between Earth and the pulsar, and so by looking at how the frequency changes, we could also try to reconstruct if there was any gravitational wave. So some people are working on this. I'm optimistic that we're going to be the first. But that's also an effort that's going on right now. We'll see. Okay, and so I wanted to get to something more specific, which is these things called gamma ray bursts. That's not going to work. How many of you have heard of these things, gamma ray bursts? At least a few of you. That's very nice. So a little bit of history. So the whole thing started not with this picture, but in the 1960s when there was a proliferation of nuclear tests. In the world, there is, by the way, an excellent YouTube video. I don't know if you guys, there's a link here, which you guys will not have, unfortunately, but there's a video that shows all the nuclear tests on Earth for the past, since it was going on for the past 7 years. It's extremely, I mean, educational. I at least would not expect it that many, and like the locations and everything. It's very, very interesting. So. Check it out if you are interested. But the point is, there was this proliferation in the 60s when there was many more nuclear tests, basically in the US and Russia, than before. And this was something that had to stop for various reasons. And there was this treaty that basically, I think in '66, that claimed that, okay, well, we have to stop these testings. And in order to ensure that nobody does this anymore, the US sent up a few satellites called the Bell satellites, whose sole purpose was to look at the Earth and basically try to catch the Russians doing tests which were not allowed. The way they did that was through detecting gamma rays. Gamma rays are very energetic photons, and the reason we can see them is that they are also emitted in nuclear reactions. When you have a nuclear fission in a nuclear bomb, many things will be emitted. One of them will be a lot of gamma rays that you can detect. So if you look at the Earth with these satellites and the Russians do something, you will see that in gamma rays. And people did this, and again, the 60s, there were these satellites. And to their surprise, what they found, well, the Russians were actually reasonably good in this sense. But what they saw was these bursts of gamma rays, not in the direction of Russia, but in completely different directions, basically, from outer space. Okay, so gamma ray emissions randomly, short time, random direction. Okay, they couldn't do anything for a while because it was all secret. But after quite a few years, they published an article saying that they observed these things called gamma ray bursts of cosmic origin. Again, it was too far from the Earth. It couldn't be anything with the Russians. So it had to be something completely different. But they didn't know what it was. They had no idea. There was no way to predict what these things were. So how could we figure out? Actually, we are still not 100% sure at this point. I would say 99.5% sure what they are. But how can we figure out what the origin is of these very strange events? Again, this is interesting because, well, for many reasons, but one of them is the higher the energy for anything that comes from any direction, the stranger the event has to be. We can't create gamma rays in normal ways here in this room, for example. It would be hard. So we can look at a few experimental evidences, what we have from this. So if we observe these things for a long time, one of the things we will see is that their direction is completely random. Or isotropic. There's no preferred direction. Just like what we heard from Cal earlier on, if you see something from any direction, the chances are it's not from the galaxy. So it has to be something from farther away. So typically, you can expect that from something random like this, it has to be extragalactic. It has to be from larger distances, which also means that it has to be a very strong event. If it was in the galaxy, if it was close, it would not need to be that strong. But if it's farther away, it can be way more energetic. So we know that because it's extragalactic, these have to be very energetic events, very energetic gamma ray bursts in this case. Another piece of evidence is their evolution in time, how the strength of the gamma ray emission changes in time. This is one image. This is the number of photons we detect as a function of time we were talking about. This is roughly a minute. Again, there's a very fast variation in time. So why is this interesting? Well, if you think about anything cosmic like stars or galaxies, etc., especially if it's extragalactic, we have to think about very large things, right? The galaxy is huge, a star is huge. And if there's something very big, it just cannot vary that fast because, again, the variation of a object cannot be faster than how long it takes for light to cross it, just like, again, in the previous talk. So just from how fast the thing changes, which is basically order of 10 milliseconds or so, we can have a size limit on how big this thing can be. And it turns out it cannot be bigger than our Earth. It's a very tiny, tiny thing, not for our standards, obviously, but for astronomical standards. Okay, so we have a very small object that has to create this extremely energetic emission. Okay, and the third evidence that was interesting or educational is that at least with some of these events, some of these gamma ray bursts in the past, I would say, 20 years, Running out of time or just leaving?
I'm not leaving.
Okay, good. For some of these events, we observed, again, in the past 20 years, it's fairly new, a joint supernova explosion, which is basically the explosion of a massive star. So there had to be, thank you, there has to be a deep connection between some massive star that's exploding, and this gamma ray burst. However, this was not observed for all, or I would say, many of the gamma ray bursts. Some of them had no such counterpart. So it turns out the longer ones had a counterpart, the shorter ones didn't. So there can be, in principle, two different objects. Again, one of them is connected to massive stars, another version may not be. And as you may have guessed in the direction of this talk, so as we think now, again, there's no proof at this point, but what we think as the most likely origin of these events is, in fact, black holes. When a massive star collapses and a black hole forms in the center, it starts basically sucking in the material that falls in from the dead star and creates an energetic emission called a jet in one direction, and that's what we observe as a gamma ray burst. The other possibility, it doesn't need to be a massive star that collapses. The case when we don't see a counterpart, we expect that that has to do something with the merger of two dead stars, again, what's closely connected to gravitational waves. So this is one of the key features, how we know how often these things may happen. We know they're connected to the emission of gravitational waves, so we can calculate how often we will, based on our sensitivity, how often we will be able to see this. And this will be the confirmation of this process, which again at this point is not certain because we can't see these things from close. Okay, we can't see how these things occur at, again, billions of light years away. With gravitational waves, we will have a much better picture of differentiating in what happens specifically. One of the complications is that even simulating these events is extremely hard. This is just a picture of a simulation to give you guys an idea. The bottom line is, if we put together a star on a computer, we can't make it explode. It's sad, but true. It's a very complicated event. There's lots of factors. Basically, one of the key things, for example, simulating magnetic fields seems to be extremely difficult. So at this point, there are lots of issues with simulations as well. So again, the best and easiest way to figure out how these things work is going to be through gravitational waves, which is excellent. So I have a final slide here. I have extra slides in case you guys want to stay for much longer, but I just want to maybe wrap up here. So again, there's a lot of interesting questions and a lot of interesting things, but basically what I want to have as a takeaway message is that well, black holes are, actually that's not what I wrote there, but so black holes are interesting for many reasons, but one of the reasons is that is not what happens when we are really close, but basically what we can learn from the universe about them, and that's through well, gravitational wave emission, and also this thing called multi-messenger astronomy, when we combine information from well, gravitational waves and other gamma rays, optical observations, etc., when we can have the fullest picture of what happens in the universe. Thank you.
Why don't we detect mid-sized black holes?
That's a good question. Again, one of the reasons
you would think black holes are being created for 13 billion years. They'd be all over the place.
Exactly. That's exactly why it's super surprising or unusual. And the main reason could be that they are not connected to other emissions that we can detect. Right. So all we know so far is from the observation of light from either matter falling in or basically stars encircling, for example, around the central supermassive black holes. So it may be that simply for the middle-sized black holes, there's no connection. Exactly.
What's the closest black hole?
We don't know because it's again really hard to see them. The closest we know of is from detecting its companion star and the sucking material. That's roughly 6,000 light years away. That's the closest one, so not really close. Again, it's very far. The central supermassive black holes in the center of the Milky Way is 8 kiloparsec, which is 24,000 light years. That's the closest supermassive. We know that for sure. So there must be things much closer, but we don't know about them at this point, again, because it's hard to see them.
Is there any known relationship to determine the size of a black hole in a galaxy based on the volume and the mass and the size of the galaxy?
It's a very good question, and there's a lot of correlations within the size and the properties of the galaxy and the central black hole, the closer connection seems to be not the size of the galaxy, but how fast or how randomly the stars move within the galaxy. So the bigger black hole ends up creating more mess in the galaxy in distance. But that doesn't mean that you need to be afraid of a black hole that's far away, just somehow there's a deep connection between the two. So that's the main way how people try to connect these two things. There's this famous relation, yeah. Okay.
Is there any speculation as to whether black holes extinguish?
There is a speculation called the Hawking radiation, which you probably have heard of. Basically, the idea is that, or let me start with saying that we have a hard time currently combining general relativity and quantum mechanics. That's one of the big open questions in physics. We have no idea how to solve this. Many of us suspect that black holes will be the way forward, but again, it's not clear at this point. But the point is, if there is quantum mechanics operating in a black hole, what ends up happening is that the mass of the black hole, which is at the very center, or close to the center, again, the circle that we see is just the point of no return. It has nothing to do where mass is in the black hole. So the bottom line is, what we suspect is that the mass which is in the center of the black hole can quantum tunnel out of the center to the outside through the point of no return. So even though nothing really can come out of the black hole, quantum mechanically, everything can go through everything, right? I could jump through this wall with some finite probability according to quantum mechanics. I'm not going to try it, but the point is, it's in principle possible. And we think the same thing is true for black holes. Mass can quantum tunnel out of the center, and if nothing else happens to the black hole, eventually it would evaporate, right? And it's continuously, supposedly, is radiating through this Hawking radiation. So the issue with this, it's a very small effect. So for these black holes, which is solar mass or higher, the effect is so small that it's never going to happen. And even if it did, the radiation that's falling into the black hole, for example, the cosmic microwave background is much more than what would be coming out. This would be, it turns out that the smaller the black hole, the easier it is to quantum tunnel out of the center. So the bigger the black hole, the harder it is. So for very tiny ones, people suspect that it wouldn't be a problem. One of the things you may have heard of was regarding the Large Hadron Collider in CERN Geneva, where somebody, I think from Hawaii, sued the detector because it could in principle create black holes, and they didn't want to die, and then they thought that would be a problem. And the reason it's not a problem is, well, you can argue different ways, and actually they would never say black holes, so they changed the name of black holes to something else as a detector to make sure nobody is scared. But the point is, even if you did create a small black hole, if it's really small enough, it would evaporate instantaneously before it could suck up anything else. So it wouldn't be an issue. But for those, this is a very important factor, so we may in fact be alive because of this evaporation.
Excuse me, could somebody hesitate to be a part of the door moving a little bit?
Antimatter?
Antimatter would not be a problem because antimatter just interacts with regular matter and it just radiates and it's bad but not too bad. In fact, it creates a lot of antimatter. Right? In fact, they tried to create antimatter. That's one of the experiments there. So, but that wouldn't kill the Earth. What would, in principle, kill the Earth or destroy it is if there was a black hole created, then it would just suck all us in. But it's not going to happen, unfortunately, because of the radiation.
I was watching a documentary on Interstellar that you commented on, and it looks like some physicists collaborated with the producer.
Yes.
Doing some simulations of the accretion disk or the light of that.
Yes.
To say that's not true, that you wouldn't be able to see any of that?
Yeah, so it's a very interesting, the movie was very interesting in many ways. Basically, so Keith Thorne was the astrophysicist. He's also in our collaboration, actually. He's also interested in black holes. His concept was that the movie should, okay, I want to be precise. He said something like, they wanted to make sure that any physical law that we all agree on is going to be complied with in the movie. So they're not going to basically break any existing physical law. But for those cases when scientists don't have 100% agreement, they can just choose one of the options. So that's supposedly what they did, and to a large extent they followed this line. There were some notable exceptions. Let me tell you maybe two examples. One example which I liked was they had this planet close to the black hole, if you guys remember. And if you were on a planet, then 1 hour on the planet was 7 years here, let's say. And well, so that in principle can happen, but in order for that to happen, the black hole has to rotate extremely quickly, basically unphysically quickly. So you could make a black hole rotate that quickly, but that could never arise from scratch in nature, because nothing would make the black hole rotate so fast. So in principle it's possible, in practice never going to happen, unfortunately. Right? So small changes. The other change is, as soon as this black hole rotates so quickly, one of the things that will happen, you will have redshift for the material that's going around the black hole. So what you're going to see, you see the accretion disk, this matter around the black hole, and you're going to see the one part that's coming towards you extremely quickly. You're going to see that blue shift because it's coming towards you, and the other part, red shift, because it's going away from you. And that would happen, and they would have been able to calculate this, obviously, but they figured that this would be too complicated for the viewers, so they didn't do it. Right? If you remember, the whole color is the same because they didn't want to confuse anybody. The same thing, if the black hole would be rotating too quickly, it would look like it's deformed, it would look like an ellipsoid, it wouldn't look like a sphere. But then again, that would be too complicated, so they ended up with a circular black hole. So again, not a big deal, small change. For the most part, they try to stick with. The library thing is not physical. I mean, that's, unfortunately, I don't want to disappoint anybody, but that's, I don't think that's reasonable. But so to a large extent, they tried to stick with what we know. And they did many simulations for the black hole part.
Earlier you mentioned that there's millions of black holes in the Milky Way. Where does that number come from?
So there's two ways to tell this. The first is that you know how many big stars are out there and how long they'll live. So you can basically calculate, for example, how many big stars have died in the past in the Milky Way, and they will have to be black holes. The black holes don't go away at this point, so they have to be there. The other way to tell this is that you have detected some black holes that are out there through their companion, right, when they're really close to their companion. And you can, even though you don't see a black hole in every, next to every star, you can just multiply how many you see because they're close, because they're in, because they are good for observation, by how many of these cases may be out there. So there's different ways to estimate this number. It's not a precise number. We're talking about roughly, I think, 100 million black holes, at least in the galaxy. So lots of black holes. Again, you can estimate it in different ways, basically by extrapolating what you know than otherwise. Good question. But again, only one very big black hole. So many tiny ones. In fact, another interesting thing is the black holes, well, they don't go away, but they don't like to be just anywhere. They actually like to stick together. They all are moving towards the center. And so if you go really close to the central black hole, there's going to be thousands and thousands of smaller ones just really close to the central one, which is an interesting aspect of this.
So all of the black holes are going towards the center?
All of them do, but okay, I would say that for the ones that this matters are the ones that are close enough that this will happen on a time scale that's of interest. Typically, in astrophysics, if something occurs on a time scale that's longer than the age of the universe, we say it never happens. It's a matter of taste, but that's the definition. So if something is far enough, yes, eventually it would move closer, but if it's 100 billion years, I don't care. So it's not going to happen.
If by chance a little black hole came wandering by us at some large radius, would you guys be able to detect it with your...
It's a very good question. So they are so tiny and they're so hard to detect. You mean with this experiment specifically, or in general?
The LIGO experiment.
LIGO. The unfortunate answer is no, because the black hole, it's not enough for the black hole to be close. It has to be accelerating. It has to be changing its speed. Okay, so you have to shake the black hole to be able to detect it. And if the black hole just goes by, it's not going to be. It's just going to go straight, right? Nothing really will happen to it very quickly.
So Kuiper will get disturbed.
Many things will get disturbed, but not on the timescale that is for which this detector is sensitive. So unfortunately, that wouldn't be the best way to identify the black hole. There would be other ways how we're looking for black holes. In fact, there's a lot of one of the easiest way to get funding for telescopes in the U.S. A piece of advice is to look for asteroids that are potentially dangerous to the Earth. So there's many very big telescopes that got funding for this particular reason, to make sure that we will notice everything that comes too close, or that would kill us like the dinosaurs. We're gonna, we don't want to do that. So it's a lot of funding for this specifically. And then they can use the observatory for science as well.
Is there any connection of this to antimatter, black holes and antimatter? Is there any connection?
It depends on what you call connection. So black holes are not, so for a black hole, it makes no difference if it's all antimatter or matter, because you fall in, and even if you only encounter the matter, antimatter, or whatever is in there once you're in there, and once you can't tell anybody what happened to you. So for any practical purpose, the black hole doesn't care about either way. So in this sense, there is no connection, which is, it may or may not be a connection, but yeah. So we don't care about antimatter at this point.
Are there black holes in globular clusters?
Yeah, of course. So everywhere where you have
is there one
massive
in the
stars
center
out.
of?
Yeah, it's a good question. No, so we don't see any. So for small enough objects, small enough clusters, there's no such thing. Many people have tried to find, for example, these intermediate black holes in globular clusters for this reason. We have no confirmed detection so far. So at this point, it seems that there's nothing in the center. It may be too small for enough matter to gather in the center, but we think that there's nothing there, which is large for sure. But a lot of people are looking at it. It's an interesting direction. No evidence so far. Many false claims. Yeah.
Well, thank you so much.
Are you just updating one of your LIGO facilities or both?
Both of them at the same time, so it works together. It can't work by itself. What's the same effort? You know, the exact same thing. In fact, you triangulate, you travel to both at the same time, because if I'm doing something, I have to build a thing.